Hi, my name is Rialda Spahic and I am a PhD candidate. The title of my PhD is Remote Operations and Future Operating Models, and I'm focusing on ensuring the reliability of unmanned autonomous systems. My PhD is a part of BRU21 program area New Business and Operational Models and is funded and supported by Equinor. The remote operations typically rely on safety support functions such as maintenance, inspection, and monitoring. And this typically involves working under poor conditions, such as low visibility areas, potentially even chemically contaminated areas. And we can remove these tedious and dangerous tasks from human operators and from the need to send the vessels offshore with the underwater drones. So far, we have seen the potentials and the benefits of using remotely operated drones for these tasks to inspect the assets, such as the underwater pipelines. But more recently, we are interested in using the autonomous drones that can reside underwater, autonomously inspect the remote assets, and even more importantly, continuously collect the data. Which begs the question, do the autonomously and manually operated drones differ in data collection, and how? To answer this question, we have set up an experiment of two identical campaigns. We have compared the exact same data collected by an autonomously run and manually operated drone by collecting environmental and water measurements. We have analyzed this data by applying anomaly detection methods that will detect noises or significant information as discrepancies in data, and the classification methods that would classify different water conditions. We have realized that these two are equally reliable for data collection. However, the data itself was imbalanced. They were underrepresented, the data classes, for water conditions, and then they were classified as anomalies and dismissed. But why is this important? Because we need to know when an anomaly is significant and when it is not. When do we trigger an alarm with an autonomous drone, and when do we ignore the situation? Sometimes we can detect biological growth, but sometimes it can be rupture or corrosion that needs immediate intervention. So this is a balance between false alarms or triggering immediate reaction responses. Which leads us to our overreaching task, is to extract valuable information on hazardous occurrences from massive amounts of imbalanced data. For this, we propose our very own warning identification framework. And this framework intends to solve several challenges. First of all, luckily for us, the hazardous events are quite rare. But this leads to their scarcity in data, and this is known as the data imbalance. Secondly, these massive amounts of data are unlabeled, which means we don't know what we are looking in this data. And thirdly, the anomaly detection and classification methods have two extreme shortcomings. They often overwhelm with the false alarms, which is the noisy and insignificant information that wastes resources, or they ignore the significant information. So we have found an overlap between these tasks and risk analysis objectives, and we are using the insights from risk analysis to semi-supervise and set decision boundaries for anomaly detection and classification. So how do we do this? We use risk analysis to give us the lists of hazards and their symptoms, such as the likelihood and the frequency of their occurrences, the consequence of their occurrence, and the sequence of events that leads to it. We input this as a decision boundary to anomaly detection to help us detect the true anomalous points as opposed to the false ones. So for external corrosion visual examination, the risk analysis tells us what symptoms to look for and what symptoms to look for in other sensor measurements. And more importantly, the consequence analysis tells us how to prioritize the response actions from the autonomous drone to not waste our resources. Once we have detected the anomaly, it is time to classify it to know what we are dealing with. Therefore, we are proposing a novel categorization of anomalies by their temporal change that we can detect within the time series data that is continuously being collected by the drone. So we are proposing the expanding anomalies with which we can follow the rate of corrosion and ruptures, reappearing and disappearing anomalies with which we can follow the biological growth, and frequent or recurring anomalies that help us differentiate the vast amounts of normal data from the potentially anomalous data. With this categorization in mind, we finally have the possibility to early recognize and react to the upcoming hazardous state. We can capture the anomalies early and follow their growth and prevent their hazardous occurrences. Within this project, we focus on more important data from the vast collections of sensor measurements. We can prioritize and understand how to set the prioritization of anomalous drones mitigation actions, and we can understand the underlying causes of anomalous occurrences. Because the reliability of unmanned autonomous systems and the safety of remote operations cannot be overemphasized. Thank you for your attention.